All right, everybody, buckle up, because today we are diving headfirst into the world of cutting-edge materials. I'm talking about the kind of stuff that'll make your jaw drop. Like, imagine a world where your phone screen could, heal itself, or your electric car charges in the blink of an eye.
And what's even cooler is that we're not talking about some distant future here. This is the very real potential of a material called Graphdiyne.
Graphdiyne, GDY. It's so new, most people haven't even heard of it yet. But let me tell you, it's got scientists buzzing. And that's what we're diving deep into today with the help of our expert, of course. So no need to go digging through those dense scientific journals. We've got you covered.
We'll break it all down so you can understand exactly why this material is so revolutionary.
All right, let's jump right in. What exactly is Graphdiyne? I mean, we all know carbon, it's everywhere, right? But this Graphdiyne thing, this is different, right?
You're right, it's different. Think about diamonds and graphite, both pure carbon, but wildly different because of how those carbon atoms are arranged. That's what gives them their unique properties.
Right.
And that's what's so fascinating about Graphdiyne. It has this whole other way of arranging carbon atoms, something called sex-ps-p2 carbon bonding, and that's where the magic happens.
Sep-p2 carbon bonding.
Yeah.
Okay, gotta admit, that sounds a little intimidating.
I promise, it's not as complicated as it sounds. Think of it like building with Legos. You've got your carbon atoms, those are your bricks, and they can connect in different ways. This particular sp2 way of connecting gives Graphdiyne some really unique properties, just like you can build a spaceship or, I don't know, a castle with the same Lego bricks just by putting them together differently.
Okay, that makes sense. So it's all about how those carbon atoms are linked up. What kind of unique properties are we talking about here?
Well, for one, this whole bonding thing creates this naturally porous structure. Think of it like a sponge, but on a way tinier scale, like a molecular level. GDY is also super stable, doesn't react easily, which is a big deal. And importantly, it has what's called an inherent bandgap.
Bandgap. Okay, now you're just messing with me, right? That sounds like something you'd hear in a music studio.
Right. But in the world of materials, a band gap, it basically determines how well something conducts electricity. Having a band gap already built in makes Graphdiyne incredibly versatile. You can do a lot with it, especially in electronics.
Okay, now we're talking. So we've got this super unique material with all these cool properties. But how do you even make something like this? It's like you'd have to build it atom by atom.
It's pretty close to that. Synthesizing Graphdiyne is complex. There are two main approaches. You've got your dry chemistry methods, and then there's wet chemistry. And within those, researchers are constantly refining all sorts of specific techniques.
I bet. That sounds incredibly detailed.
Oh, it definitely is.
Could you give us an example of one of those techniques,
Yeah.
just to wrap our heads around it?
Of course. One really interesting method is called Q-surface-mediated synthesis.
Q-surface. Does that mean copper is involved somehow?
Exactly. Imagine a copper surface, almost like an envelope, and we're talking super tiny here, obviously. But basically, the GDY is grown directly on that copper, so it acts as both a catalyst, kind of helps things along, and a template, so the GDY forms with the right structure.
It's mind-blowing to think about this happening at such a tiny scale. What about the wet chemistry techniques?
One that's particularly fascinating uses the interface between two liquids, kind of like where oil and water meet. The GDY forms right at that boundary.
That's incredible, almost like it's magically appearing. Okay, so we've got what makes Graphdiyne unique, how it's made, but I think everyone's really wondering, what can this stuff do? All right, let's get to the really exciting part. We're talking potential applications. This is where Graphdiyne goes from being interesting to a total game changer.
It really does. And its potential spans so many fields. But let's start with something everyone can relate to, energy storage. Batteries, to be specific.
Okay, yeah. Everyone wants a better battery, am I right? My phone is always dying.
Isn't that the truth? Well, GDY, with its unique structure, it could be the key to batteries that charge faster, hold more energy, and last longer.
All right, now you've got my attention. How does that even work?
Remember those pores we talked about in GDY's structure? Well, those actually create these pathways for lithium ions to move through super efficiently. And that means faster charging and a higher capacity for energy storage.
Wait, so you're telling me no more waiting like an hour for my phone to charge?
That's the idea, but it gets even better. GDY's structure, it also helps prevent those pesky dendrites from forming.
Dendrites, what are those again?
So dendrites, they're these tiny branch-like lithium deposits that can build up in batteries over time. They interfere with the flow of electricity, can shorten the battery's lifespan. even be dangerous in some cases.
Oh, wow. I didn't realize it was such a problem.
Oh, it's a big one in battery technology. But the good news is GDY's structure, it makes it really hard for those dendrites to form, so you get safer, more reliable batteries overall.
That's amazing. So safer A&D, longer-lasting batteries. Okay, what else can this wonder material do?
Well, it also has huge potential in the world of catalysis.
Catalysis. Now, remind me what that is again.
Basically speeding up chemical reactions. Think of a catalyst as like a matchmaker, bringing those molecules together in just the right way to make something new.
Okay, I get it. So how does Graphdiyne fit into all of that?
So GDY's structure, particularly that special sp2 bonding we talked about, it makes it an ideal platform for creating these super efficient catalysts. We call them atom catalysts. And they can really maximize those chemical reactions while minimizing waste.
That sounds incredibly useful, especially for things like, I don't know, clean energy, reducing pollution, that sort of thing.
Exactly. And speaking of clean energy, GDY might be able to change how we produce hydrogen fuel.
Hydrogen fuel. Now there's something I have heard of. That's supposed to be a big part of the whole clean energy future, right?
It really is. It's super efficient, clean burning. The only byproduct is water. And it turns out GDY can actually help us produce it.
Okay, how?
Yeah.
Because I don't know a ton about it, but it seems like water is pretty stable stuff. You need a lot of energy to, like, rip it apart.
You're right. Splitting water to extract hydrogen takes energy. But GDY can actually act as a catalyst in two different ways to help with this. First, there's electrocatalysis. It uses electricity to split those water molecules.
Okay, so using electricity to rip those molecules apart, that makes sense.
Right. But here's the cool part. GDY can also facilitate photocatalysis, which means using sunlight to power that same reaction.
Whoa, hold on. So it can work with both electricity and sunlight.
Exactly. It really highlights just how versatile Graphdiyne is, and that versatility, it extends even beyond energy. We're seeing some exciting research in the biomedical field as well.
Biomedical. Okay, now we're switching gears completely. How does GDY even apply to medicine?
Well, researchers have found that GDY actually interacts with cells in a very unique way. So they're looking into its potential for things like cancer therapy and new antibacterial treatments.
Okay, my mind is officially blown. Better batteries, cleaner energy, potential medical breakthroughs. Are we done yet? Is there anything GDY can't do?
We're not done yet. Remember that whole bandgap thing we talked about, how it relates to conductivity? Well, that same property makes GDY incredibly sensitive to changes in its environment. We're talking like really sensitive. And that makes it perfect for developing advanced sensors.
So we're talking like a super sensor then. What could it detect?
Things at insanely small scales. For example, GDY sensors could potentially detect changes in humidity, which would be huge for agriculture, weather forecasting, you name it.
That's wild. It's like having a microscopic weather station.
Exactly. And it doesn't stop there. Remember how we talked about biomedicine? This sensing ability also makes GDY incredibly promising for biosensors, which could be revolutionary for medical diagnostics.
Wow. So what you're saying is we have a material with the potential to, like, change everything from how our phones work to how hospitals operate.
You're getting the idea. And honestly, we're just scratching the surface here.
This all sounds almost too good to be true. Are there any downsides to Graphdiyne? Anything holding it back? It really does sound, I don't know, almost too good to be true. We've talked about all this amazing potential, but are there any challenges, like hurdles that are slowing things down? The Graphdiyne revolution, is it on hold?
Well, we're still in the early stages. I mean, unlocking GDY's full potential, that's going to take time, right? And one of the biggest things right now is just scaling up production.
So getting it out of the lab and into our hands.
Exactly, exactly. Those synthesis methods we were talking about, they're amazing, but they're complex.
Yeah.
And they're expensive.
Yeah.
To make it, really affordable, accessible, we need to figure out how to produce it on a much larger scale, way more efficiently.
So that's the challenge right now, making it more readily available.
That's a big one. And honestly, as those production methods get better, it'll be so interesting to see what new applications come up. Because the more we learn about GDY, the more potential we uncover.
That's so true. We've covered a ton of ground today in this deep dive. For our listeners who are just catching up on the amazing world of Graphdiyne, what's the, key takeaway you'd want to leave them with?
I think the biggest thing is that Graphdiyne, It's not just a new material, it's a whole different way of thinking about material science. It's not just the individual applications, but what it represents, this one material with the potential to change so many different fields, and we're just starting to understand how.
Like we're on the edge of like a new materials age.
Yeah.
We've got electric cars now, smartphones, all this cool tech. Now imagine what those could look like once we really tap into the power of Graphdiyne.
Exactly. And it's not just about making what we already have better either. GDY could be the key to, I don't know, some of those really big challenges we're facing, like cleaner energy, more effective medical treatments.
Now that's an inspiring thought. This deep dive has been amazing. We went from self-P2 carbon bonding to self-healing phone screens and revolutionizing entire industries. I'm not sure where else we could have even gone today.
It is incredible, Graphdiyne. And, the most exciting part, we're just at the beginning. Who knows what other groundbreaking materials are out there?
That is what makes science so cool. Always something new to discover. So to everyone listening, keep your ears open, keep that curiosity alive. The future of material science is wide open, and Graphdiyne is just the beginning. Thanks for joining us for this incredible deep dive. Until next time, keep exploring.